Okay, the topic for this video is finding solutions to definite integrals. Just a reminder, everything we've done up until now is on indefinite integrals. A second thing to know is that if you're taking a real calculus course, this method that I'm about to show you in today's video is called the fundamental theorem of calculus. Now, first of all, what's the notation difference between definite and indefinite integrals? Well, this is a indefinite integral. So if you write this with the squiggly thing here of 2x dx, this is pronounced indefinite integral of 2x with respect to x. By comparison, if you just put a number on the bottom here and a number on the top, this becomes a definite integral. So this notation here is spelled out or is pronounced as the definite integral of 2x with respect to x from 1 to 4. Okay? So the last thing you say are the boundary values from lower boundary to upper boundary. Second thing to remember is that in terms of actual interpretation, the definite integral is the area under the curve. Now, in terms of actually calculating in terms of calculating a definite integral, it's a fairly straightforward two-step process. The first step, if you start with this a equals definite integral from a to b of f of x dx, the first thing to do is to find the general solution for the indefinite integral of f of x dx. So notice that I took away the boundary values here. So the first thing you need to do is actually do an indefinite integral. You forget about the c at the end, and we'll call this indefinite integral, the answer that you get at the end of it, we'll call that capital F of x. So just to go continue with my example of definite integral from 1 to 4 of 2x dx. So if we start with this, first thing we need to do is calculate the indefinite integral of 2x dx. 2 comes out. Apply the power rule, so this becomes, this is x to the first power, and so taking the integral of it, it becomes x squared over 2, and you can forget about the plus c, and so this in turn becomes just x squared. So that's the indefinite integral. Okay? But you're not done yet. That's just step 1. Step 2 is take that answer that you got, in our case the x squared, evaluate it at the upper boundary, evaluate it at the lower boundary, and then take the difference between the two. So substitute b into the indefinite integral, substitute a into the indefinite integral, and then take the difference. So for step 2, I'll do that in orange here. Step 2 would be to take x squared and evaluate it at 1 and 4. And again, the reason I use 1 and 4 is because those are our boundaries on the original function here. This is the short way of writing evaluate x squared at 4, evaluate x squared at 1, take the difference between the two. This vertical line here, that's the shorthand. What this really means is 4 squared minus 1 squared. 4 squared is 16, 1 squared is 1, and so our final answer is 15. Now remember, back in the very first set of videos, I told you that indefinite integrals give you functions, whereas definite integrals give you numbers. And so at the end of every definite integral, as long as you have real boundaries here rather than variable boundaries, you should get an actual number. All right, let's apply this to a few different sample problems. want to make sure I only take one sheet at a time, that way I don't run into that bleed-through problem I had on the last video. Alright, so definite integral from 0 to 7 of 3x squared dx. First step is to consider integral of 3x squared dx. Alright, this is no addition or subtraction, so we just move the constant outside. So integral, wow, this is starting to get really messy. Alright, 3 times the integral of x squared dx. Integral of x squared dx is x cubed over 3. So this is 3x cubed over 3. And ordinarily we would put the plus c here, but we don't have to worry about that for a definite integral. Alright, next thing we need to do is we need to take this function and evaluate it at each of the boundaries. Oh, sorry, we need to do a little bit of simplification first, so this just comes out to x cubed. Nice and convenient there. Alright, so now we need x cubed. Oh, I should switch colors here. Now we need x cubed evaluated at 0 and 7. Same boundary values I had up here. Okay, so we get this, which becomes 7 cubed minus 0 cubed. Well, 0 cubed is easy, that's 0. 7 cubed is 49 times 7, 49 times 7, let me get a calculator. Go. $343. And so 343 minus 0 is, not surprisingly, 343. Just a reminder, well, that's a good enough answer. Actually, that's a perfectly good answer. Just a reminder as to what this means in real life. If you were to take a typical Euclidean plane here and draw the function 3x squared, which is a parabola, then what I just asked you to calculate is this area here. So this area that I'm shading right now, this is 343 units, or 343 square units, I should say, because it's an area. Alright, so that's what the definite integral means. It's not too hard, right? Just do the indefinite integral, evaluate at the upper boundary, subtract the same function evaluated at the lower boundary. Alright, well, this was easy because we started with an easy function. Let's start with a slightly more complicated function. Alright, if we start with this, then we need the indefinite integral of 6x to the 5th minus 19x cubed plus square root of 2x minus 4 dx. Okay, so all I did is I chucked away the boundary values for now. Okay, we got stuff, 4 different functions added or subtracted from each other. So the addition and subtraction property says we can distribute the integral across these various functions. So what we end up with is integral of 6x to the 5th dx minus integral of 19x cubed dx plus integral of the square root of 2x dx minus integral of 4 dx. Okay, take each of these and apply the power rule. This one will take a little bit of algebra to do first, but these others we can handle with the power rule right now. Alright, so integral of this integral, we can factor the 6 out. this integral, we can factor the 19 out. And let me do a little bit of algebra here. Square root of 2x is the same thing as the square root of 2 times the square root of x. And here, 4 is the same thing as 4 times the integral of x to the 0 power. Alright, I'm not going to change any of these except for this one with the square roots. So I'm just going to copy this down. And this term. No changes so far. Okay. Square root of 2 might not look like these other constants, but it is in fact a constant. So you can pull the square root of 2 outside the integral. And then, let's rewrite this as x to the 1/2 power. Okay, now we can apply the power rule to all 4 terms. Integral of x to the 5th is x to the 6th over 6. Integral of x cubed is x to the 4th over 4. Integral of x to the 1/2 is x to the 3/2 over 3/2. And integral of x to the 0 is just x. And ordinarily we'd put a plus c out here, but again, we're doing a definite integral. That's what the boundary values tell us, so we don't have to worry about that. Alright, now we've gotten rid of all the integral signs and all the dx's. All we need to do now is a little bit of algebra to clean things up. Okay, so the 6's cancel out. 19 is a prime number. And we get 2 times the square root of 2 over 3 times x to the 3/2 power minus 4x. Alright, so step 1, done. Step 2 is to evaluate our answer to step 1 at our 2 boundary values. Now, this happens to be relatively easy because one of our boundary values is 0. It would be even nicer if our other boundary value was 1. Guess I got no one to blame but myself for that. I'm the one who makes these problems. Okay, so remember what the vertical line with the 2 boundary values on it means is to evaluate at the top number, evaluate it at the bottom number, and then subtract the difference between the 2. This is going to get kind of messy, but it'll get cleaned up real quickly after that. Alright, so substitute in a 2 wherever we see an x. Then substitute in a 0 wherever we see an x. Now I put these square brackets around it because you have to evaluate everything inside the square brackets first and then subtract it from our initial upper value term. Alright, well the good news is that all of this stuff in here, all of this second set of square brackets, that becomes 0. Anything times 0 is 0. Alright, 2 to the 6th, let's see, 2 squared is 4, 4 squared is 16, let's see, 16 times 2, that'd be 32. Let me just make sure I'm right on that. No, I'm wrong. 64. Okay, so we got 64 minus 19 divided by 4 times 2 to the 4th power. That's 76 plus 2, raise it to the 3 halves power. Actually, you know what? Let's work out the rest of this, the rest of this stuff. All right, 2 times the square root of 2 divided by 3 times 2 raised to the 3 halves power. Don't forget to include the 3 halves in parentheses since it's in an exponent. Alright, let me just double check here. 2 square root of 2, 3, 2, okay, good, this looks right. Alright, this is going to give us 2 2/3. Minus 4 times 2, that's easy, that's 8. Okay, let's get all this math to get done. 64 minus 76 minus 8. Okay, so not counting the fraction, we get negative 20 plus 2 2/3. And so that's going to be, let's see, that's the same thing as adding 3 and subtracting 1/3. So that's going to be negative 17 1/3. You can convert this to an improper fraction if you want, but this mixed number is just fine. Alright, so that's 2 examples. I'll go through a bunch more examples in the next video.